Okay, so basically this is the statement of Gauss's law. So if you are asked in the exam to write down Gauss's law, this is what you have to write. And this is the mathematical expression. As I told you earlier also, that whenever in the exam you are asked to give some definition or you are asked to write down some law which includes a mathematical expression, then don't forget to include the mathematical expression giving the symbols. Okay, so that is something you must always do in, at least in science subjects like physics and chemistry, because you know the examiners have to check a number of transcripts. So if you just write this, it is difficult for him or her to read each and every word. But if you write this and then give the mathematical expression along with it, and box it or highlight it, then the examiner will see it and he or she is satisfied. This guy knows the law, and then probably he'll just check through the writing to see whether you've written it properly or not. So it's a good way of getting the marks required. Anyway, so this is the statement of Gauss's law, and we were trying to get an insight into what this law tries to tell us. Okay, so for that, consider a positive charge, isolated positive charge plus Q, and we know that for an isolated positive charge the lines of force will be moving outwards, radially outwards in all directions like this, right? So if we imagine a surface of radius capital R surrounding this charge, the surface is not there, we are imagining it to be present for our purpose. So this is a surface of radius capital R with its center at Q. Spherical surface, of course, because this is a three-dimensional picture. I can't draw a 3D picture on my slide, so you have to imagine that this is a point charge. Isolated point charge means lines of force are coming out from it in all directions, radially outwards. So this surface surrounding the charge is a spherical surface, okay, not circle, it's a spherical surface. Now, what is the surface area for this sphere? It is 4 pi capital R square. Alright. Now, the total number of lines of force that come out from Q, P capital N, then the number of lines of force per unit surface area of this sphere is N by 4 pi R square. Okay. This much I think is clear. Let us now consider another spherical surface with double the radius. Okay, again centered at Q. So this green sphere now with radius twice R. So what is the surface area of this green sphere? 4 pi into 2R whole square, so 16 pi R square. And what will be the number of lines of force passing per unit area for this outer sphere, that is the green sphere? It will be N by 16 pi R square, because N remains same. We have not changed the charge. So the charge is same, so which means that the number of lines of force coming out from the charge will still be N. Earlier it was N, now also it will be N. But the number of lines of force passing through the red sphere, that is the smaller sphere, is definitely larger than the number of lines of force passing per unit surface area of the outer sphere, that is the larger sphere. And we can see clearly that the density of the lines of force for the green sphere is 1/4 of the density of lines of force for the red sphere, right? So basically what does this tell us? That as we move far away from the charge, the strength of the electric field will decrease. The density of the lines of force is proportional to the magnitude of the field. As we move further away from the charge that is creating the field, the density of the number of lines of force will decrease. And it is clear from the picture also. The density of the lines of force for the red sphere is definitely more than the density of the lines of force for the green sphere. However, see, You all know, we just saw what the field due to a point charge is. So the field due to the charge Q at a distance capital R from it, which means that at any point on the red sphere, on the surface of the red sphere, the value of the electric field is Q by 4 pi epsilon naught capital R square. Whereas the value of the electric field at a distance 2r, that is at any point on the surface of the green sphere, is Q by 4 pi epsilon naught 2r whole square. Understood? But if you multiply the magnitude of the electric, definitely the field at any point on the green sphere is lesser than the field, the magnitude of the field, I mean, is lesser than any point on the red sphere. The value of the electric field at any point on the green sphere is lesser than its value at any point on the red sphere. So the field is weaker on the green sphere, the field is stronger on the red sphere. So the more we are close to the charge, the stronger is the field. However, now if you multiply the electric value of the electric field with the surface area of the sphere in consideration, that is, for the red sphere, this is the red sphere, if you multiply E with A, then basically you are multiplying Q by 4 pi epsilon naught R square with the surface area, that is 4 pi R square. The answer is Q by epsilon naught. If you do the same multiplication for the green sphere, E into A, so now it will be Q by 4 pi epsilon naught twice R whole square multiplied by 4 pi twice R whole square. So again we are left with Q by epsilon naught. Alright, so you see, if you look at the highlighted quantity Q by epsilon naught, although we are at different distances from the charge, we know that the strength of the electric field is different at these 2 points. When we are on the red sphere, the field is stronger. When we are on the green sphere, the field is weaker. But if you take the product of the electric field with the total surface area of the sphere on which you are trying to calculate the field, you will see that the value of the product remains unchanged. So you can draw infinite number of spheres around Q of different radii, but whichever sphere you are on, if you multiply the magnitude of the field on that sphere with the area of that sphere, the product will give you the same result, and that is Q by epsilon naught. So although the density of lines of force changes with distance from the charge, although the strength of the field changes with distance from the charge, but there is this one quantity, that is the product of the field with the area of the surface at which you are trying to calculate the field. That product always remains the same, and it does not depend on the distance. It depends only on the total enclosed charge. Okay, so this product is known as the flux of the electric field. The product of the magnitude of electric field with the area of the enclosing surface, and the flux will be determined only by the enclosed charge. It does not depend on the distance at which you are calculating. It depends only on the value of the enclosed charge. So no matter how far you are or how near you are to the charge, the flux will remain same if the charge remains, enclosed charge remains unchanged. So this is exactly what Gauss's law tells us. Okay, now we will go to the formal proof of Gauss's law. So, you know, in the exam, if you are asked to prove Gauss's law, you don't have to write all these. But I made this particular slide only to make you understand what is the exact meaning of the Gauss's law and what is the meaning of this quantity flux. I wanted to show you how flux remains unchanged and how flux depends only on the enclosed charge. Okay, so now we will go over to the formal proof of Gauss's law. So if in the exam you are asked to prove Gauss's law, then these are the steps that you should follow exactly. Okay, usually the marks allotted will be say 4 or 5 to prove Gauss's law, but you have to follow each and every step, and you know, you can't leave it in between. You will see how I uh, you know, derive the expression at the end. So what do? Let us consider a closed surface enclosing a volume V. Earlier, when we, in the earlier slide, when we drew the sphere surrounding the charge, we drew a sphere, so it was a regular surface. Now let us consider any arbitrarily shaped closed surface S which encloses a volume V. Okay, so this is, you have to consider the three-dimensional picture which I cannot draw on a slide. So this is an arbitrarily shaped closed surface which has surface area S, and it encloses a volume capital V. So it can enclose a volume only if it is a three-dimensional surface. So don't think this is a plane. This is a 3D surface which encloses a volume V. I hope that is clear to everybody. Please don't think this is a plane. This is not a two-dimensional picture. This is a three-dimensional picture, and it is a enclosure, not a plane area. It is an enclosure which has a volume V. Okay. If the surface is a regular one, then you can think of a sphere or a closed cylinder or a cube. But for the most general derivation, we will consider any arbitrarily shaped surface. We will show that Gauss's law is valid for any arbitrarily shaped surface. Now, we have a single point charge Q which resides in the interior of S. A single point charge Q is there inside this surface Q. Okay. Let us consider an elemental area, very small, infinitesimal area ds on the surface S at a distance r from Q. So this is an elemental area ds. The arrow, the green arrow, shows you the normal to the surface, so that gives you the direction of the area, and it is placed at a distance r from Q. Okay. Now obviously the electric field at this area due to the charge Q will be along R. Electric field is in the same direction as R. Remember, we had calculated this earlier. Electric field will be in the direction same as that of R. So this is the direction of the electric field. And let us consider that the angle between between E, which means between R and ds, is theta. So this is the angle theta. Is this picture clear to everybody? Can you just check and tell me if I need to explain this once more? I hope this picture is clear to everybody. Can someone please unmute? Yes?
Yes,
Oh,
ma'am.
okay. Okay, good.
Yes,
Okay, so
ma'am.
I'll continue. Okay, so now we just discussed what flux is. Flux means magnitude of the field multiplied by the area through which the field lines due to that particular field is passing. So flux of the field E through this elemental area ds is given by the product of E into the component of ds along E. Okay, so d phi, as we had defined earlier, is the dot product of E and ds. So it is E ds cos theta. Okay, magnitude of E multiplied by magnitude of ds into cosine of the angle theta between them. So the total flux of the electric field due to the point charge q through the entire surface. How will we get it? Flux d phi through just this elemental area, that is infinitesimal area ds, is this. So how will you get the total charge through the entire area S, surface area S? You will integrate this, plain and simple. So total flux is obtained by integrating d phi, that is integration E dot ds or integration E ds cos theta. But we know that E is equal to q by 4 pi epsilon naught r square. The value of E at any distance r from a charge q is given by q by 4 pi epsilon naught r square. So we can write phi equal to integration, in place of E we write q by 4 pi epsilon naught r square into ds cos theta. Now q is a constant, 4 pi epsilon naught is a constant. So we outside the integration. So we have q by 4 pi epsilon naught integration ds cos theta by r square. Okay. Now this integration ds cos theta by r square can be written as integration d capital omega, where d omega is the solid angle about the position of q. So if you just take d omega here, see, this is a cone. If you take this elemental area ds and draw lines and join the edges with the point at which the charge is residing, okay, so basically you get a conical shape whose angle is, three-dimensional angle is d omega. Okay, so this is known as the solid angle. This is a concept of coordinate geometry which you may have encountered earlier. Solid angle you should have come across earlier. If not, you can just look up any geometry book. The angles that we talk about are two-dimensional angles. When we shift to three dimensions, then we talk about solid angles. Now the angle subtended by this elemental area ds at the position of q, which is at a distance r from the area, is d omega, and its expression is given by ds cos theta by r square. Okay, so ds cos theta by r square is d omega. Now if you integrate it over this entire surface, so basically you are spanning the entire volume. So what will be the total value of the solid angle? It will be 360 degree, that is 4 pi. Okay, so integration d omega for the entire volume is always equal to 4 pi, the total solid angle about the position of q. Okay, so here in place of integration ds cos theta by r square, we can write 4 pi, because the value of this integration is 4 pi. That is what we just understood from the concept of solid angle. So for any point charge inside the surface S, phi equal to E dot ds, which we can write as equal to E dot n cap ds, where n cap is the direction of the normal to the surface, is equal to q by 4 pi epsilon naught multiplied by 4 pi. 4 pi is for this integration ds cos theta by r square. So 4 pi and 4 pi goes, we are left with q by epsilon 0. Remember in the qualitative discussion also, in the earlier slide we had obtained the flux is equal to Q by epsilon naught. So we can write, for a single point charge inside the enclosure with surface area S, E dot n cap ds, which in other words is the flux, is equal to Q by epsilon naught. Now don't think that Gauss's law ends here. Okay, and when you are asked to prove Gauss's law in the exam, please don't end your answer here because it is incomplete. Why? This is for just a single charge. Now, if you have an enclosure, it is not always the case that there will be only one charge inside. There may be more than one charge. There may be several charges inside the enclosure. Then doesn't Gauss's law apply for several charges? Does it apply only for a single charge? So we'll see that just now. So now consider that S has a bunch of charges inside of values Q1, Q2, Q3, Q4, etc., Qi up to Qn. N can be any number, okay? So that same surface S enclosing the volume V. But now we have several charges, Q1, Q2, Q3, Q4, Qi. This can go on, whatever be the number of charges inside, okay? So by the principle of superposition, the total electric field due to all these charges should be the vector sum of the individual electric fields. So the total electric field E is equal to E1 plus E2 plus E3 plus etc. plus Ei. That is summation Ei goes to 1 to n, where n is the total number of charges. Therefore, in the expression integration E dot n cap ds, we write in place of E the resultant. E is the resultant. So we write it as E1 plus E2 plus E3 plus etc. whole dot n cap ds. So we can just separate out these integrations. Integration E1 dot n cap ds plus integration E2 dot n cap ds plus etc. plus integration Ei dot n cap ds. Understood? Because each is separate, so we can just separate out the integrations. Now, from Gauss's law, we know that integration E1 dot n cap ds is Q1 by epsilon naught, because E1 is the field due to Q1. Integration E2 dot n cap ds is Q2 by epsilon naught, because E2 is the field due to Q2. And similarly for all the individual charges. So for single charges, we have found out what Gauss's law gives us. So from Gauss's law, this is Q1 by epsilon naught. This is Q2 by epsilon naught. This is Qi by epsilon, right? So when we separate out the individual fields using the principle of superposition for each of the charges, we can apply Gauss's law for each single charge, because we have already proved Gauss's law for each single charge. So now this therefore can be written as, since the denominator is the same epsilon naught, so we can write the numerator as sum I equal to 1 to n Qi, that is the total sum of all the charges, and this can be written as Q enclosed by epsilon naught. So E dot n cap ds for several charges is capital Q by epsilon naught, where Q is the total charge enclosed within S. This is the complete proof. So if you are asked to prove Gauss's law for, say, the question is like this: state Gauss's law, prove Gauss's law for an enclosure with surface area S and volume V. Okay, then these two slides, whatever is there in these two slides together, that you have to give. You cannot stop at the proof for a single charge. You have to, if it is said that there is a single charge, then you can stop there. But if it is a general question, then you have to give the proof for the total enclosed charge. And this is how you will come to the conclusion. Is it clear to everybody? Is this much clear to everybody?
Yes, ma'am.
Okay. So I'll stop the class here. We still have some more discussions on Gauss's law, and then we'll do the applications of Gauss's law in our next class. Meanwhile, I'll upload up to here in the college LMS, and also I'll upload the class on YouTube as usual. Okay. So please go through the notes